Hi, welcome to Vectors Day 2. I thought we could start with a reminder of the stuff that we learned in Vectors Day 1. So if I have a vector v whose initial point is 1, 5, and whose terminal point is 3, -1, I want to A, describe v in component form. Well, we said last time that uh, to get the x component of our vector, we're going to do terminal x minus initial x. And so for us, that's going to be 3 minus 1, or 2. So the x component of our vector is 2. What about the y component of our vector? So to find the y component of our vector, we do the terminal y minus the initial y. And for us, that's going to be -1 minus 5, or -6. Okay, there's the component form of our vector. What about the magnitude? Magnitude of v? Question mark. So here we want to use the Pythagorean theorem. 2 squared plus -6 squared equals magnitude of v squared. 36 plus 4 is 40, so the magnitude of v is the square root of 40, which of course we can simplify to 2 root 10. All right, so that's magnitude and component form. What if we had asked C to describe the vector in special unit vector form? And since I've inadvertently erased my my initial and ending and terminal points, let's start with these. The initial point being 1, -2, and the terminal point being 3, 5. Okay, so 5 minus a minus 2 is 7. There's the y component of the vector. And what about the x component of the vector? 3 minus 1 is 2. In component form, we'd write 2 comma 7 with component form brackets. But with special unit vector form, we write 2i plus 7j equals v. Okay, and again, we can find the magnitude of this vector by using the Pythagorean theorem. What if and I know the magnitude of this, magnitude of v will be the square root of 53. What if I want to go in this direction, but I want the unit vector in this direction? This vector is much bigger. It has a magnitude much bigger than 1. We only want to go 1 in this direction. Remember, if you want the unit vector in the direction of v, we do v divided by the magnitude of v. So our vector then, the unit vector in the direction of v, would be 2 root 53 I plus 7 over root 53 j. There's the unit vector in the direction of. And finally, the last thing that we had talked about yesterday, or in the last video rather, was how do I do v in the direction of w with the given magnitude. So I'll say that W equals 1, 4, and I'll say that the magnitude of V equals 7. So I'm looking for V in the direction of W. We said yesterday that equivalent vectors, or in the last video, equivalent vectors could be written this way. But we want V in the direction of this equivalent vector, so we're going to multiply both sides by the magnitude of V. So now, in order to use this recipe to find V in the direction of W with the given magnitude, I'm going to need to find the magnitude of W. So I use the Pythagorean theorem on these components, and I get square root of 17. So for us, 1, 4 square root of 17 over 7. Or root 17 over 7, comma, 4 root 17 over 7. This is V. It goes in the direction of W, but it has a different magnitude of W. So that's where we were yesterday. Oh, and I guess I could write this in special unit vector form and say, okay, that's going to be root 17 over 7i plus 4 root 17 over 7j. These are the same vectors. They're both vector v in the direction of w. One is just describing the vector with special unit vectors, and the other is using component form. Well, today I want to actually address a third way of describing a vector. A third way of describing a vector. So that third way requires us to say v equals the magnitude of v times cosine theta v comma sine theta v. That's the component form version, but wait, there's also a special unit vector form, which would be magnitude of v cosine theta v I plus sine theta v j. In either case, you're going to be distributing the magnitude of v to this component form or to this special unit vector form. Now, you may say, well, Mr. Cuckoo, why do we need this? We already have two other methods for describing vectors. Well, it turns out when we start doing word problems, this is what I most often use. This is a very useful tool. By the way, theta here, theta v is the direction angle. Before we get into these, let's take a step back and talk about vector v. Let's go with this vector, 1, 4. And I can draw a picture of that. I go over 1 and up 4. And there's vector v. This is 1, this is 4. Well, I want to talk about this angle. Let's call this theta v. Theta v. How can I find that angle? Well, I see here a convenient right triangle. And I've got two sides. I always have the opposite and the adjacent, so I'm always going to be using tangent theta v equals, in this case, 4 over 1. If I want to find theta v, I'm going to need to do the inverse tangent of both sides of this equation. Remember, inverse trig functions undo trig functions. So theta v equals tangent inverse of 4. I would then pull out my calculator. I think you should probably have your calculator set in degrees for this inverse tangent of 4, and I get 75.964 degrees. 75.964 degrees. So that's theta v, the direction angle. And again, we can find the magnitude of v simply by doing the Pythagorean theorem. So there are these three elements that show up a lot, especially in word problems. Those are the component or special unit vector form of the vector, the magnitude of the vector, and the direction angle of the vector. All right, now let's go back to this conversation up here. I wanted to introduce this, and the homework questions say, find the magnitude of v and theta v in each case. All right, so here's the problem that they give us. They say v equals 3 cosine 30, comma, sine 30. Okay, and so many students want to do stuff here. They want to distribute. They want to figure out what the cosine of 30 is. But read the directions. The directions just want us to identify what the magnitude is. We know the magnitude is this number out in front of the component form. This is the magnitude. And they want us to identify theta v. Well, theta v is this angle that's in with the cosine and the sine. The angle that's in with the cosine and the sine is 30 degrees. So magnitude of v equals 3 and theta v equals 30 degrees. Like I said, vector math is really easy, but we really have to pay attention to the vocabulary and pay attention to what we're being asked. Okay, so if I had seen v equals 4 cosine 45 I plus sine 45j, and I was asked what are the magnitude and direction angle in each case. Again, my magnitude of v in this problem is this number out in front, 4, and theta v is the angle here with both of these trig functions, 45 degrees. Now, with the same directions, we could get more challenging things. Don't get me wrong. For example, v is given as minus 5i plus 4j. 4j. Okay, so I know that the theta v, if I draw a picture of this, I go back 5 and down 4, and there's my theta v. And so I can say tangent inverse. Wait, I go up 4. Bad drawing. There we go. Up 4. Still theta v here. Okay, so inverse tangent of 4 over negative 5. If I do the inverse tangent of negative 4 divided by 5, or negative 0.8, I end up with negative 38.659, or actually 660 degrees. Now wait a minute. I got a problem here. This angle isn't negative 38 degrees. This angle is negative 38.66 degrees. My angle is this angle. So when you get a negative angle, add 180 degrees. Okay, so if I add 180, I end up with theta v equals 141.340 degrees. I think it's really important to draw these things to get a sense of what's going on, because you could easily be lulled into the wrong angle. All right? Don't be afraid to think, and sometimes drawing a picture can help us with that thinking. All right, remember the other thing we needed to do was to find the magnitude of v, and we said the magnitude of v would be the square root of negative 5 squared plus 4 squared which is 16 plus 25, or square root of 41. So here, given this special unit vector form, we were able to find the direction angle and the magnitude of that vector. Okay. What about v equals 3, 4? Okay, so I know how to draw that vector. I go over 3, I go up 4. There's v. And what do I need? I need the magnitude of v, which I can find with the Pythagorean theorem. 3 squared plus 4 squared, take the square root, and I get the magnitude of v is 5. And then I also need theta v. And there's theta v there. This is 4, this is 3, and so I'm going to say the inverse tangent of 4 over 3. I'll pull out my calculator, and I'll do inverse tangent 4 divided by 3, and I get 53.13 degrees. What's theta v, the direction angle? At what angle does this vector go off at? I know it goes over 3 and up 4. That's the direction, and this is the angle for that direction. Okay, so those are different ways that I can describe or identify theta v. Now, next thing I want to talk about today is what happens. They would like me to find the component form of v given theta v equals 30 degrees and magnitude of v equals 10. Well, we have this convenient recipe for v that I mentioned a few minutes ago, which was that v is the magnitude of v times cosine theta v, comma, sine theta v. So let's plug in what we know. We know the magnitude is 10. We've got cosine of 30, comma, sine of 30. Often these are unit circle values so that we can go quickly and use our unit circle knowledge. Root 3 over 2, comma, 1/2. And then don't forget to distribute the 10. So v is going to be 5 root 3, comma, 5. Now, if I do the Pythagorean theorem on these, I'll end up with 10. And if I do inverse tangent of 5 over 5 root 3, I'll end up with 30 degrees. So it's a nice big circle we could go in. Maybe you should try one. How about magnitude of v equals 3 and theta v equals 120 degrees? You might want to pause the video now and try this one. Okay, with the same setup, I know that v equals magnitude of v cosine theta v, comma, sine theta v. And so I'll plug in what I know. I know the magnitude is 3. I know the cosine of 120 and the sine of 120. And so that's going to be 3. Cosine is negative 1/2. Sine is root 3 over 2. And then distribute the 3. And so our component form is negative 3/2, comma, 3 root 3 over 2. Component form of v. Now, in these problems, you could as well, instead of being asked for the component form of v, you could be asked for the find the special unit vector form in each case. And so if I know the magnitude of v equals 4 and theta v equals 150 degrees, right? I'm thinking about this vector over here, whose magnitude is 4, with 150 degrees. I'm trying to describe this vector, and I'll use the magnitude of v. No, I'm doing special unit vector form. Cosine theta vi plus sine theta vj with parentheses. And so I've got 4 cosine of 150 I plus sine of 150 j. Well, we know the cosine of 150 is negative root 3 over 2 I plus the sine of 150 is 1/2 j. And then I want to distribute my magnitude. And so I end up with negative 2 root 3I plus 2j. There's our special unit vector form of v. You could also run into problems that say find v given the magnitude of v equals 8, and v is in the direction of I plus 3j. Okay, so if I think about using v equals magnitude of v cosine theta vi plus sine theta vj, in order to make this formula work, not only do I need the magnitude, but I need this direction angle. Now I have the direction I'm headed off in. I can draw that picture, go over 1 and up 3. I want to head in this direction, but I want with this magnitude. And in order to make this work, I'm going to need to know theta v. So I'm going to have to use my inverse tangent inverse 3 over 1. So I pull out my calculator, I do inverse tan of 3, and I get 71.565 degrees. So v equals 8 cosine 71.565 I plus sine 71.565 j. Okay, so 8, let's store that in x. I want 8 cosine x, and that gives me 2.5230 I plus the sine of 71.565 times 8 sine x, then I get 7.589 j. Okay, so I had to find the direction angle with this given information to make this work. What if instead of special unit vector form, they say find v given the magnitude of v is 6 and v is in the direction of 2, -3. Now we're given component form, and I think about using v equals the magnitude of v cosine theta v, comma, sine theta v, with component form brackets. Again, I have the magnitude of v, but I don't have theta v yet. How do I find theta v? Why don't you try pausing the video and seeing if you can finish this problem, and then when you're done, start the video again. Okay, so I have to find theta v, and I know I have a little triangle here where I go over 2 and down 3. That's theta v, 2, negative 3. So theta v is going to be the inverse tangent of negative 3 over 2. Okay, if I do inverse tangent negative 3 divided by 2, I end up with negative 56.31 degrees. Theta v equals negative 56.31. Okay, so yeah, I can describe that as negative. However, it's inside the triangle, and so I really think it's positive. But for the purposes of writing this component form, I want to use this negative angle. Okay, so then v would be 6 cosine negative 56.31, comma, sine negative 56.31. Okay, so let's do 6 cosine negative 56.31, and I get 3.328, and I'll do 6 times the sine, 6 sine negative 56.31. And I end up with negative 4.992. And so there's the component form of v. Okay, so we can use this recipe either working with component form or special unit vector form. And as I said before, this shows up in quite a number of word problems, especially vectors together. Okay. How about you practice this one? Magnitude of v equals 10. Theta v equals 240 degrees. And write v in component form. Okay, pause the video. Welcome back. So I've got v equals 10 cosine 240, comma, sine 240. We know the cosine of 240 is negative 1/2, and the sine of 240 is negative root 3 over 2. I distribute the 10, and I get negative 5, comma, negative 5 root 3. There's v in component form. All right. Now, completely different type of problem is what I want to head to next. Well, not completely different. It's actually an extension of this. It's adding vectors. Yesterday, or in the last video, we said that if vector v was 3, negative 2, then vector w was negative 1, 4, and we want r equals v plus w. All we have to do is add these component forms. We add the x components, we add the y components, and we end up with our resultant vector. We even showed how if we drew go over 3 and down 2, v, and then when we get to the end of v, we draw w, which goes left 1 and up 4. Left 1 and up 4. There's w. There's v. Or we could do w, which goes left 1 and up 4. There's w. And then from there, we could go over 1, 2, 3, and down 1, 2. And so we get there. And so either v plus w or w plus v. And we said yesterday, or in the last video, that the resultant vector would be this one. This is our resultant vector. And notice where we end up. This is the point 2, 2. So we would describe r as being 2, 2. And we can get that either by reading it off our graph in this case, or simply by adding the x and y components together. Well, what if we're given this vector information? The magnitude of u equals 2 and theta u equals 30 degrees. The magnitude of v equals 3 and theta v equals 45 degrees. And what we'd like to find is r, which is the result of u plus v. And not only do I want to find the component form of r, but I also want the magnitude of r and theta r. I want all three of these things. So let's start off by building vector u. U will be the magnitude of u times cosine theta u sine theta u. And v is going to be the magnitude of v cosine theta v sine theta v. Okay, so let's plug in what we know, and then we'll add those. So we've got 2 cosine 30 sine 30, and we've got 3 cosine 45 sine 45. And we want to add these together. Well, I can't add these, and I can't add these. I have to do some more math first. So let's go do some math. We know the cosine of 30 is root 3 over 2, and the sine of 30 is 1/2. And we know the cosine of 45 is root 2 over 2, and the sine of 45 is root 2 over 2. When we distribute the magnitude in each case, I can get to component form root 3 comma 1 and 3 root 2 over 2 comma 3 root 2 over 2. So here's u, here's v described in component form, and we're looking for r, the sum of them. Once we have r in component form, I also want to find the magnitude of r, and I want to find theta r. Okay, so let's go. If I add these vectors together, the x component is root 3 plus 3 root 2 over 2, comma, the y component is 1 plus 3 root 2 over 2. Many people don't like having these radicals, and they would prefer to decimalize things. I'm fine with that. Just don't forget to close those parentheses when you do these radicals, or you'll be getting the wrong values. Square root of 3, close parentheses, plus 3 square root of 2 divided by 2. And so I get 3.815, no, 853, comma, and then over here, 1 plus 3 square root of 2 divided by 2. Then I get 3.121. So there's the component form of r. Remember, I also wanted the magnitude of r. And I find the magnitude of r by doing the Pythagorean theorem. And then taking the square root of both sides. So 3.853 squared plus 3.121 squared, and then take the square root of that answer. And I get that the magnitude of r equals 4.958. Oops, not degrees. And then finally, theta r. Well, if I draw this, what I'm saying is I'm going over 3.8, and I'm going up 3.12, 3.853, and I'm looking for theta v. Again, Theta v is going to be found with the inverse tangent of 3.121 over 3.853. I think a common mistake on tests with this material is people put x values over y values even though they're doing tangent because these x values come first. You know you're doing inverse tangent because you're looking at the picture. Draw the picture, label the picture, then think about the inverse tangent. You're less likely to make a mistake that way. Okay, so let's do inverse tangent of 3.121 divided by 3.853. And I end up with 39.008 degrees. And in my mind, that kind of makes sense because remember, we started with one vector that went off at 30 degrees and another vector with a bigger magnitude that went off at 45 degrees. And so if I do this vector addition, my resultant vector is this one. There's my resultant vector, r. And I can see that that angle is between the 45 and the 30. And this angle is between the 45 and the 30. I also see that the magnitude should be bigger than the magnitudes of either of the others. That's not always true, but it's certainly true in this situation. And I can see that when I draw the parallelogram. It may help you to draw the parallelogram. Okay, so will you please try finding r, the component form of r, magnitude of r, and theta r, given the magnitude of u equals 4 and theta u equals 30 degrees and the magnitude of v equals 6 and theta v equals 120. Remember, u plus v equals r. And we're looking for the magnitude of r, magnitude of r, component form of r, and the direction angle for r. So pause the video, come back when you're done, give this one a try, and let's compare. Okay, welcome back. I've got u equals 4 cosine 30 sine 30, and v equals 6 cosine 120 sine 120. And I want to add those. Well, I know that cosine of 30 is root 3 over 2, and sine of 30 is 1/2. And with v, I know the cosine of 120 is negative 1/2, and the sine of 120 is root 3 over 2. When I distribute the magnitude in, I end up with u being 2 root 3, comma 2, and v being, don't lose that negative, negative 3, comma 3 root 3. If I'm adding these vectors together, I can describe r 2 root 3 minus 3, comma 2 plus 3 root 3. But most people end up using their calculator and saying 2 square root of 3, close parentheses, minus 3 is 0.464, comma 2 plus 3 root 3, 2 plus 3 square root of 3. And that is 7.196. So there's our component form of r as decimal. Now what about the magnitude of r and theta r? Well, for magnitude, I'm going to do Pythagorean theorem with these. And for theta r, I'm going to do inverse tangent with these. So let's set those up. Okay, magnitude of r, magnitude of r is going to be the square root of 0.464 squared plus 7.196 squared. I'll do that on my calculator. 0.464 squared plus 0.7 plus 7.196 squared. And then take the square root of that. And I end up with the magnitude of r equals 7.211. Now what about theta r? Well, theta r, we've been using inverse tangent to find. Tangent inverse the y component, which is 7.196 over the x component, 4.464. So on my calculator, inverse tangent, 7.196 divided by 0.464, and I get that theta equals r equals 86.31 degrees. Okay, there we go. Feeling comfortable with this yet? Well, let's do one more, just because this is what all the word problems are like, or most of them. How about magnitude of u equals 20, and theta u equals 150, and magnitude of v equals 30, and theta v equals, how about 60? Okay, so, we can think about this as we've got one force headed this way, and we've got another force headed this way. And we want to know where this object ends up going. When we apply these two forces on this point, what happens? The resultant vector is what happens when we add these two forces together. It's sort of like your friends pulling you in two different directions, and you end up going a third way. Well, let's figure out what that third way is. We can sketch it because we know how to add vectors visually, and from our initial point to our terminal point, that's going to be our resultant vector. So I have a visual understanding of what I'm going to. I'm expecting an angle a little bigger than 90 degrees for my resultant vector. Okay, let's see how it all works out. You can certainly pause the video and try this one out, and then we can compare. Let's see. So u is 20 cosine 150 sine 150, and v is 30 cosine 60 sine 60. So we want to add those, but we can't add them until we tidy them up a bit. So 20 cosine of 150 is negative root 3 over 2. Sine of 150 is 1/2. Ooh, I drew the picture wrong originally. It shouldn't have been down here, it should have been up here. And so we've got that one and that one. I still think I'm going to get an angle bigger than 90. Negative 1. Negative 1? No, positive 1. Okay, there's u, and v is 30. Cosine of 60 is 1/2. Sine of 60 is root 3 over 2. Distribute the magnitude in each case, and so I get negative 10 root 3, comma 10, and here I get 15, comma 15 root 3. And this is what we want to add together. R could be described as 15 minus 10 root 3, comma, 10 plus 15 root 3. Or we could decimalize everything. 15 minus 10 root 3, negative 2.321, comma, 10 plus 15 root 3 is 35.981. So there's our resultant vector in component form. To find the magnitude of r, I'm just going to do the Pythagorean theorem with these. 35.981 squared plus negative 2.321 squared. Take the square root, and I end up with the magnitude of r is 36 point, I think that's an 8. No, it is 0. 0.056. Okay, and then, hey, one other thing. You know, if these magnitudes are pounds of force, then this is pounds of force. If this is miles per hour, then this is miles per hour. If these are miles, then these are miles. Our magnitudes can represent all kinds of different quantities. Okay, and then finally we need theta r, and to find theta r, we're going to be using inverse tangent. Tangent inverse of 35.981 over negative 2.321. Okay, so if I do the inverse tangent of 35.981 divided by negative 2.321. Hey, and before I hit enter, cosine, the opposite over adjacent, right? So I'm thinking about, I'm going this way 2, and I'm going up 35. So when I hit enter, I get a negative angle. This is negative 86.309 degrees. What's up with that? Well, remember there's a restriction on inverse tangent. It only gives us values between negative 90 and 90. And I said before, when you end up with this negative angle here, when you really want this positive angle here, you better add 180 to it. No one's going to tell you to do it, but what you just found was this angle. You don't want that angle. You want that angle. So add 180 plus 180, and I end up with theta r equals 93.691 degrees. Okay, so what's next? Well, believe it or not, I have a little more to cover. What if I want to find the same stuff, r, theta r, magnitude of r, but this time I'm told v equals I minus j, and w equals 2I plus 2j, and I know that r equals v plus w. Well, we can easily get that special unit vector form simply by adding 3I minus plus j. There's r in special unit vector form. If I want to find theta r, you know, there I can understand this as going over 3 and up 1. And there's my theta. There's 1, there's 3. So I'm still going to use inverse tangent of 1 over 3. Inverse tangent of 1 over 3 is theta r equals 10.435 degrees. And then finally we want the magnitude of r, which we can use the Pythagorean theorem to find and come up with the square root of 10. So this seems a lot less labor intensive than those other ones because I'm already given the component forms. The direction angles are already worked into these problems. Why don't you try one? Again, we know that R equals V plus W. We're looking for R, we're looking for magnitude of R, and we're looking for theta R. Okay, so let's say that V equals 3I minus 2J, and W equals 2I plus J. So, you might want to pause the video now, give it a try. Okay, I'm adding these two together to get R. I get 5I minus J. And the magnitude of R is going to be the Pythagorean theorem used here. Square root of 5 squared plus negative 1 squared, or square root of 26. And then finally, theta R is going to be tangent inverse of negative 1 over 5. Now, let's think about this. Here's V. V goes over 3 and down 2. Here's W. It goes over 2 and up 1. If I add these two vectors together, I get this parallelogram. And if I draw the vector from the initial point to the terminal point, this is going to be my resultant vector. So when I do this inverse tangent, I'm looking for what angle? That angle. That's my direction angle. And so I expect that angle to be a negative angle. So we'll do inverse tangent. Oops, wrong electronic device. We'll do inverse tangent of negative 1 divided by 5. And I end up with negative 11.310 degrees. Negative 11.310 degrees. There's my direction angle. Excellent. Okay, there's one last thing to talk about, and it pulls in our conversation from last week about law of cosines. So now we're told, hey, you've got some forces acting on an object. Force 1 is 20 pounds. Force 2 is 30 pounds. And you've got the resultant vector, Fr, of 25 pounds. And what we're asked to find is, what's the angle between force 1 and force 2? Okay, so if I try and sketch this, and I don't have component forms, I just have magnitudes here. Let's clarify. Magnitudes. Given magnitudes. So one has a magnitude of 20, the other has a magnitude of, in fact, we'll make it really easy. We'll go 20, we'll go 30, and we'll say this magnitude. There's Fr, and so the magnitude of that resultant vector is 25. Now some of you are saying, Mr. Kukla, this is the hypotenuse in that right triangle, and it's actually longer than that side. And I agree. I'm not drawing this to scale. And yes, it is possible to have that be shorter than that magnitude. And you'll run into that in the next couple of homework assignments. So don't be surprised when it comes. Okay, so how are we supposed to do this? Well, let's envision a triangle with some forces and a resultant force. And cut this one down. So here we go. And what I'm suggesting is that rather than draw the picture this way, I really want to think about that parallelogram. Here's force 2, here's force 1, 1 plus 2, or 2 plus 1 gets me to here. So I'm saying if this is 20, if this is 30, or at least the magnitudes of these forces are 20 and 30, and now I've got the magnitude of this force is 25. Well, the cool thing about knowing the law of cosines is we can use side, side, side to help us find an angle. Now, ideally, I'm looking for the angle in between force 1 and force 2, but that's split into two separate pieces, and I don't even know that they're congruent pieces. So instead, what I'm going to do is I'm going to find phi, and I'm going to say, okay, cosine phi equals 20 squared plus 30 squared minus 25 squared over 2 times 20 times 30. So I've got 400 plus 900 minus 625 divided by parentheses 2 times 20 times 30, and I get cosine, not theta, but phi, cosine phi equals 0.5625. Remember, we don't want the cosine of this, we want phi itself, so we need to take the inverse cosine of both sides. So inverse cosine, and now we've got that phi equals 55.771 degrees. This angle is 55 degrees. Aha, this angle is 55. And what do we remember about theta and phi's relationship in a parallelogram? Because we talked about this in law of cosines. We said that these were same side or consecutive interior angles, and they were always supplementary. So we know that theta plus phi should add up to 180. So if we're looking for theta, the angle in between the two vectors, we're going to do 180 minus phi. And in our problem, 180 minus that angle we just found is 124.228 degrees. 124.228 degrees. Now, let's think about drawing that picture. Okay, so we've got one force that goes 20, and another force, no, I want that one to go 30, and a force to go 20. And what I'm saying when I draw my parallelogram is the resultant vector's angle is 124.228 degrees. Okay, nice. So, law of cosines. Let's try another one. Let's say force 1 equals 8, force 2 equals 10, and force resultant is 16. So I start by thinking about the magnitude of, these are all magnitudes. Magnitudes, magnitudes. I've got 8, I've got 10, and then I add those vectors together, and I get this resultant vector whose magnitude is 16. These are congruent. I can then find phi by saying that cosine of phi is 8 squared plus 10 squared minus 16 squared all over 2 times 8 times 10. So we get 8 squared plus 10 squared minus 16 squared, and we want to divide that number by 160. And so I get cosine phi equals negative 0.575. Therefore, phi is the inverse cosine of that, or 125.0996. We're going to call that 0.10 degrees. 125.10 degrees. And therefore, theta is 180 minus phi, 180 minus that angle, and we get 54.9 degrees. That's our resultant vector's angle, theta r. Okay, great. And we've got the magnitude of r. And if I really wanted to, I could write the component form of r. Sorry, that's not 54 degrees. This is 54 degrees because theta and phi add up to 180. So this one, the angle in between the two forces, is this. Yeah, I don't want to try and do the component form of that. Okay, so that is what we're going to be looking at in the next homework assignment. I hope that goes well for you, and I look forward to seeing you in our next video. Have a great day, everyone.